As promised, today I will talk about energy and momentum conservation. Whether I throw a ball in Austria, Japan, or the US, it looks the same, even when I compare different times. In the textbook, this is referred to as homogeneity of space-time, which causes energy and momentum conservation. I remember this fuzzy phrase well because it made conservation laws extremely mysterious to me. But assuming you are familiar with functional variations, the derivation is not that hard. So buckle up, here comes Noether's theorem for the case of variations in space-time. Assume we have a system in terms of some Lagrangian, which is a function of a scalar field phi, and its derivative. So let's define exactly what is the derivative. Here I used a common 4-vector notation. We see that phi must be a function of x. The Lagrangian, as it is not directly dependent on time. This is true for all microscopic systems and hence a good assumption. We now apply a variation in space-time and want to know how this changes the Lagrangian. The variation of the Lagrangian can be expanded by means of partial derivatives and variations of the fields it depends on, so phi and its derivative. Note that the variation is a linear operation, so it can exchange positions with the derivative. We will use this for the second term. Also recall Euler-Lagrange equations, so that we can rewrite the first term. These nicely symmetric terms can be collected in one expression via the inverse product rule. The last step is to expand the variations of phi, so the result is written in terms of the actual variation, delta x. Keep this result in mind for a moment and follow a second thought. The variation of the Lagrangian can also be written directly by taking the derivative with respect to x. In order to make the indices look the same as our previous result, we sneak in a delta that is 1 when mu equals nu. And to make it look even more alike, the derivative ought to go over the whole expression. It is clear that the delta is constant in x and hence makes no difference. But could you show the same for delta x nu? Stop if you want to try. So here you go. Combining our two results yields a conserved current, meaning that the derivative vanishes. This happens for all continuous symmetries, as proven by Emil Noether about 100 years ago. That's why this current is generally called Noether's current. We derive the special case for variations in space and time, where the continuous symmetry is the homogeneity of space-time. While the whole expression in brackets is the Noether current, we already observed that the variations of x can be arbitrarily included or excluded from the derivative. So the more interesting quantity in this case is the tensor T mu nu. This is the energy momentum tensor. To interpret the components of this tensor, it is best to look at nu equals 0 and expand mu in temporal and spatial components. It yields a continuity equation where we recognize the Hamiltonian as the Legendre transformation of the Lagrangian. So this is the change in energy density minus the flux of the energy density that vanishes. Analogously, we can set mu equals I, meaning the space coordinates. In this way, we find a continuity equation for the momentum density. Therefore, in any volume in space, the energy is constant over time or passes through the surface. And in any volume in space, the total momentum is constant over time or passes through the surface. This is exactly like the continuity equation in electrodynamics, where charge in a volume is either conserved or passes through the surface as flux. From this, we are motivated to also define the Noether charge. Still comparing to electrodynamics, it must be the integral over the zeroth component. For time variations, Noether's charge is energy, and for space variations, it's the total momentum. I hope that made things clear. I did suppose you know about Euler-Lagrange equations that follow from Hamilton's principle, and calculus like variations and four-vector notation. If that was strange to you, you may want to check out the description below. Thanks for watching, that's pretty much it. See you next time!